lecture on thermal remote sensing. Till now, you must be aware of the optical remote sensing and the features which are identified using the reflected radiations. And what we see from the optical remote sensing is the reflected radiation, and which depends on the different wavelengths, which defines by the spectral signature of an object. So hence, to visualize or understand the objects using the optical remote sensing, so we use the multispectral wavelengths, whether on the ground or the space. And the another type of radiation that the body has, the emission, that is when it is heated up, so it emits. So at a particular temperature, so what happens is at a particular temperature, the radiation happens, and that is sensed by the so that is sensed by the sensors. So so as you can see from the figure, that the white light, this light from the sun, when it is emitted from the sun, it interacts with the earth surfaces, and the absorption or the reflection and the transmission happens, and the reflection determines the color of the object. So all the bodies, as you know, that all the bodies are above absolute zero, that is minus 270 degrees centigrade, emits radiations. So the body gets heated up, and then it also emits the radiation. And this radiation happens in the long wave infrared, that is the thermal infrared. And the maximum emission at a particular wavelength determines the property or the color of the object. And this emission happens day and night, because the depending on the temperature, this emission happens the maximum emission happens at a different wavelengths. Also, you know that the energy transfer mechanism happens in the form of the convection radiation. So you must be knowing the conduction, that is the transfer of the heat by in contact. So from one molecule to another molecule, the heat is transferred. Molecules are not moved, but the heat transfer happens. Convection is the mass transfer of the medium, and the radiation happens from in the vacuum. So the emission happening from one object and sensed by the sensor, whether on the ground or on the space, we are concerned with the radiation. So this transfer happens in radiation, and the radiation happens in the vacuum, because if you say the sun and the earth, so there are in between there is a vacuum. So all the energy transfer happens via the transfer of the photons, energy transfer via photons, and this travels through vacuum. And you know that the maximum energy, that is the velocity of light, is maximum in the vacuum. So the energy transfer happens with the velocity of light. Now you know that the sensors that measure the emitted radiations in the thermal infrared can produce another important distinguished signature. So indirectly, we try to assess the signatures of the object or the properties of the object over the earth surface. And there is a concept of the black body. One should understand that black body is an ideal thermal emitter that transforms the heat energy into the radiant energy with the maximum that is rate permitted by the thermodynamics law. Similarly, the black body also absorbs all the incoming radiant energy and converts into heat energy regardless of any wavelength. So that's the maximum permissible limit of the emitted radiation is governed by the black body. So the interaction of this light or this white light with the matter and the details of the nature of light was well explained by Max Planck. And you see this is explained with the equation derived by Max Planck, famous known as Max Planck equation. So this is nothing but that is the how much energy is emitted from that is a black body, how much emission is emitted from a body at a particular temperature and at a particular wavelength. So if we know the temperature and if we know the particular wavelength, so we can calculate the amount of radiation emitted from the body. And this is applicable for black body. As I said, this is maximum, that is the upper limit of the radiation of the radiance of the material. So that is governed by the black body. So for example, when you have seen that when an iron rod is heated up, so it changes its color from so it becomes red, then becomes reddish orange, then blue becomes blue. So depending on the temperature, as the temperature increases, that is the maximum, that is the energy which is emitted from the iron rod surface governs the temperature, or indirectly from the color we can judge the temperature. So that's the equation which is given by the Planck's law. But that is body should be black body. Now this relation, or the black body relation between the temperature and the radiance is best suited to understand the energy distribution not only of the Earth's features but also from the far distance any heavenly bodies or stars or galaxies in this space. Also, it is derived, that is the maximum energy or the maximum energy at a particular wavelength is determined from the Planck's law given by the famous law which is known as the Wien's displacement law. So it is the first derivative of the Planck's law. It means that if the energy is distributed, so what will be the maximum energy at what wavelength? So that will be given by, derived from the Wien's displacement law. So if you see that, so lambda max, that is which is the maximum wavelength at which the maximum energy will be emitted. So that's given by K by T, where K is 2898 and depending on the temperature in Kelvin. So for example, if you see here, sun temperature is around 6000 Kelvin. So temperature is 6000 Kelvin. So if we plot it, so the maximum, so this 6000 Kelvin, so the maximum energy so emitted will be at 0.48 micrometer. So this will be the maximum energy. If you say, for example, the Earth, 300 microns, 300 microns, oh sorry, 300 Kelvin. So if you see the 300 Kelvin, so the maximum energy will be around 9.6 or 9.7 microns. So this is the maximum energy. For example, if there are other features, for example, there is a fire on the Earth's surface, so it will be around 800 to 1000 Kelvin. So it will be around, if you see 800 Kelvin, it will be around 3.5 micron. So, or 3.6 micron. So this is the maximum energy. So depending on the maximum energy curve, this curve, one can design the sensors which can sense the maximum amount of, so we can tap the maximum amount of energy. So that sensor, that wavelength of the sensors or the waveband of the sensors or the spectral band of the sensors, one can design so that it suits to capture that particular spectral region. And that is a particular temperature. So if we integrate the Planck's law from lambda 1 to lambda 2, that is one wavelength to another wavelength, that is spectral nature of the wavelength. So that becomes the Stephen-Boltzmann law. So for example, over the Earth's surface, the maximum, the energy, if you see this curve, the energy is from the 8 to 14 microns from, this is the 300 Kelvin. You see this is 300 Kelvin. So around 8 to 14 microns. So most of the features, they are emitting their radiation in this spectral nature. The maximum energy is tapped here. So this becomes when, so one has to calculate what is the total amount of the radiance from 8 to 14 microns. So that will be governed by integration of for each of the Planck's law. Planck's law gives the radiation at a particular temperature. So for example, if you want to integrate from this region to this region, so we have to integrate all the Planck's equation. So that becomes the Stefan-Boltzmann. So area under that curve becomes the, so area under that curve becomes the Stefan's, determine the Stefan-Boltzmann equation. So as I said, the so what happens is the black body is an ideal body, but on the Earth surface we don't find the really the black body. So most of the bodies, they don't emit, or the upper limit of the as compared to the black body, so it is less than the black body. So the efficiency is less than the black body. So that that parameter is known as emissivity. So the emissivity is the efficiency of a material with which it emits as compared to the black body. So for example, 300 Kelvin, take the same curve, 300 Kelvin. So this is the maximum energy that is emitted from a black body. So if there is a real body, for example, what is the, here it is around 50, for example, 50 watts per meter square. Say for example, 9.7, at 9.7 microns, that is 50. So if it is a real object, for example, not a black body, real object on the surface, the emission will be less than this. For example, it will be 40. So that is 40 divided by 50. So around it will be 0.8. So that will be emissivity. So that is the efficiency of the material with which it emits as compared to this black body. So that is the efficiency. So over the Earth's surface, we do not have the black body materials. So we have a real body, so real material. So it is written here, real material. So which do not emit as effective as the black body. So we define as a real materials. So if you see in this figure, so black body means the emission will be same throughout any wavelength. So the efficiency is the spectral emissivity, that is efficiency will be same. So efficiency is similar for the black body. Now real object, real bodies or the selective radiator, we say that for each wavelength, this will vary. For each wavelength, it will vary. So that is the real materials or selective radiators. So for example, if we take a small spectral band, so we can say that, for example, 10 to 11 microns, so we can say that in this spectral band, it is not changing. But from 8 to 14, or for example, 3 to 20 microns, that is a thermal channels, so this will vary from one band to another band. So real materials emissivity or the selective radiator varies with the wavelength. Then another is the gray body, which means that it will be constant for a particular for all the wavelengths, but its efficiency is less than that of the black body. So I repeat it. So emissivity of the black body is 1, emissivity of gray body is less than 1, and the emissivity varies according to the wavelength is your selective radiator or the real material. So this is for some values of some of the materials. For example, you see the water, the emissivity is 0.99. It means its emission efficiency is near to the black body, right? So for example, if you see the soil, it is 0.9, grass is 0.97, wood is 0.9. If you see the metals, it is very less. So it is very, very less, and so on. Also, the Kirchhoff's law, what it says is that the materials are good absorbers are good emitters. It means that the reflectance, the absorptance, and the transmittance. If we say this is 1, so what happens is for most of the objects in the thermal infrared, the materials are opaque in nature, so they become 0. So reflectance plus the absorptance is 1, and we say that absorption and emissivity is same. So we say that this and this is 1. So it means the reflectance is complementary to the emissivity. So it means the emissivity is 1 minus reflectance. So therefore, the reflectance is 1 minus emissivity. So if reflectance is high, so emissivity or absorption will be less, or vice versa. What it means, for example, water surface. So water is 0.99. So it means the reflectance is how much? 0.01. So near to 0. So the absorption is highest, meaning that reflectance is less. That's why in the optical remote sensing images, one can see that water reflectance is very less. So that's why it appears as dark or black in color. Also, in this one, I need to make a point that there are different types of temperatures also. So, different types of temperature. So one is the kinetic temperature. So that is the temperature what we measure by contact. That if we, like thermometer, when we touch a body or when it comes in contact with the body, so it gives the kinetic, that is because of the kinetic motions, it measures the temperature of it. So that is the kinetic temperature. But from a sensor, what we measure, from a sensor, it is very difficult to have a concept of the kinetic temperature. So it measures from the emissions. So that becomes a radiant temperature. So radiant temperature that is calculated from the Planck's equation. So we inverse the Planck's equation to get the temperature. And but the kinetic temperature and the radiant temperature are never equal, because when we measure the kinetic temperature, so we assume that it is in the thermal equilibrium, but the radiant temperature or the radiometric or the radiant temperature are because that materials are not in homogeneous or not in the isothermal nature. So hence the radiant temperature will never be equal to the your kinetic temperature. Another important terminology what we come across is the brightness temperature. So this brightness temperature is what? That is the temperature of the black body which has the same level of radiant temperature as observed at the satellite sensor level. So what it means that the materials what it emit, it captures by the sensor or the satellite sensors in the sky, and we use the same Planck's equation, inverse that Planck's equation to get the temperature, which is assumed to be emitted from the black body. So it is comparable to the emission as compared to the black body. So that temperature that we get from the inverse of the Planck's law is the brightness temperature. So then this brightness temperature is not the actual temperature, because this temperature what we got from the equation is the black body temperature, but actual real body materials are not black body. So we have to correct this brightness temperature to true surface temperature or true temperature of the surface. Now we will see some of the thermal properties of the material, because what happens is over the Earth's surface, it is very complex because it is mixture of many materials, and what we sense over a pixel, it is a composite of many materials. So indirectly, what we can say, what we can understand is the through the property of the material or the signature, thermal signature of the materials, we can determine the properties. So what are they? They are, of course, one is emissivity, as I said, then the heat capacity, and the thermal inertia and thermal conductivity. So the primary objective is to understand the nature of the composition of the material over the Earth's surface. So what is heat capacity? So that is the amount of heat required to raise the temperature of a given object by 1 Kelvin, right? So it means that if the heat capacity of the material is high, it means it will give the amount of heat required to change its temperature will be very high. So it means if the heat capacity of the material is high, so it will take more heat or more time to raise its temperature, and similarly vice versa also. Then thermal conductivity, the rate at which the heat passes from one end to another end, or pass through the thickness of the material. Thermal inertia. So as the word says, inertia, it means the resistance. So it means it measures the resistance offered by the material in undergoing the thermal changes. What it means? It means if the thermal inertia of the material is high, so it will resist more to raise its temperature. So the difference of the temperature will be very less. For example, water body and sand. So water has high thermal inertia as compared to sand. So it means during the daytime, the water will take more time to raise its temperature than the sand. So in daytime, what will happen? The temperature of the sand is higher than the water. So and night time, what happens? Again, as I said, the property will remain the same whether day or night. So it means it will resist the change in the decrease in the temperature of the water. So water body will have a less decrease in temperature than the sand. So sand will cool down more fast than water. So at night time, water will have higher temperature than sand. So these type of temperature changes or the thermal properties, we can understand the different characteristics of the feature, or we can understand at unknown area what type of feature it will be. So this thermal inertia depends on the thermal conductivity, that is the how much the rate at which it passes through the thickness. Thermal conductivity also it depends on the heat capacity and also on the density of the material also. Then the question arises that why we need to understand all these, because so in order to understand as I said, the different material unknown area, and also if you want to understand the diurnal variation of any features on the Earth surface. So diurnal variation means that is the variation of the surface temperature with respect to time. So whether it is a in a day different hourly variation, or a daily variation, or a weekly variation, so that is that variation one can understand. Property will never will remain the same. Property will be the same, but only we can see depending on the thermal properties. For example, if you want to understand study the heat flux, the energy balance fluxes, energy balance studies, the evapotranspiration, the soil moisture estimation. So every day or every hourly variation we can see. Most of the geological mapping, so we require diurnal variations. Urban heat island effects, that is the rate of change of the between the city area in the cities, how fast it is varying. Wildlife monitorings, because day and night if you want to see the movement of the wildlife, so using the thermal cameras or the thermal sensors, what we can do on the ground itself. Some are on the sensors on the satellite, or you can also mount on a ground sensor, so the property will remain the same. Of course, the apparent thermal inertia. So if you use the satellite remote sensing data, so it is an indirect mechanism where we can understand the thermal inertia. So that is known as the apparent thermal inertia. So in this, the maximum and the minimum radiant temperature, it can be measured using the satellite data day and night. So delta T, so day and night temperature variation, and with the albedo, one can use to infer the on the apparent thermal inertia. So if we see, these are some of the characteristics of some of the materials, like for example, rocks and soil, vegetation, water, damp terrain, and some metallic objects. So if we see the diurnal variation, so this is 24-hour from midnight to midnight, and how it varies from when the start of the sunrise to sunset. So the rocks and soils during the daytime, as I said, it has low heat capacity or low heat inertia, thermal inertia. So it raises its temperature very fast, and then during the after the sunset, it also cools very fast. But if you see the water, it resists. That is a change in the temperature, and because and then also it will also resist its cooling. So at night the temperature is higher for the water, and at the daytime the rocks and soil or the bare soil are high in temperature as compared to water. Similarly, the damp terrain. Now, in the thermal infrared region, which is around 3 to 20 micron, so we see that there are certain wave bands where the atmosphere permits the emission very easily without less absorption. Of course, the absorption is less, but there are some culprits like water vapor, CO2, so ozone. So they absorb some of the emissions. So there are some atmospheric windows. So these atmospheric windows, which you can see here, 3.5 to 4.5 to 5, 8 to 14. So these are some atmospheric window where the sensors are designed so that it has less resistance to the emission. And another important aspect is that during in this spectral regions, we have the small reflected component also with emission. So when we use this spectral band, so we have to correct we have to remove the small reflected component of the during the daytime. It enters here, but in this region only the emissions is there. There is no reflection, because we know that the sun radiation energy is very low in this region. There is negligible. There is no energy in this region, so there will be no reflection. So, and also between the 6 to 7 microns here, during the in the 6 to 7 micrometer, there is absorption of water vapor. So this problem also becomes a to help us to determine understand the level of water vapor in the atmosphere. So in fact, it becomes is a helping tool to understand what is the water vapor density, or the cloud information, or the cloud physics, or indirectly the rain or the rain rate. So this 6 to 7 microns is generally used in our the meteorological application sensors for the weather monitoring, alert and the forecasting. Some of the applications of the thermal infrared. So there is a vast number of applications. Some of them I have listed here. These are from the geological side, geological structures, soil moisture studies. As I said, the soil moisture, evapotranspiration, the hydrology, the sea surface temperature, the potential fishing zone, because the fish catch and all that. So one can design, or depending on the temperature variation and the other parameters, one can see the potential fishing zones, oil spills, the modelings aspects. Of course, the volcanic activity, one can temporarily see and assess the temperature and the vent of the volcano. Forest fires, of course, the stubble burning or the forest fire, or any type of biomass burning. Of course, the coal fires, the environmental aspects, meteorology, as I said. Of course, in many medical sciences, the surgeons, doctors, they use different kinds of equipments, which senses because of the thermal. Because our organs have a different temperature. Depending on the different temperature, they sense different organ using the instrumentations which has a high thermal sensors. Of course, the veterinary sciences, because the behavior and the nature of the behavioral nature of our and different animals, whether what is the problem, whether they have a disease or any kind of behavioral aspects. So one can watch day and night through these thermal cameras. Of course, there is a vast area for intelligence and military applications. This is not our aspect here. Then, as I said, the urban heat islands, the heat fluxes, the artificial heat fluxes and all that, because of the different materials in the urban areas. So they also contribute to different types of fluxes, whether it is a sensible heat or is a latent heat. So that aspect also one can study. Of course, there are many others. These are some of the glimpses. If you see, these are on the ground, the thermal cameras. And if you see these two pictures, you can easily visualize that it is a nighttime thermal camera and one background and your foreground. So easily you can identify the foreground features depending on the temperature variation. This is the these two figures are the visible and the thermal infrared. So we can see the crown cover of a tree, but someone is hiding in between the crown tree. So we can, in the thermal camera with the temperature variation, we can see this is homogeneous background and this is the body temperature of the person. Similarly, this is also visible and infrared. So one can also artificially color it, because this is black and white. So one can, depending on the different colors, one can give an artificial color to it. These are some examples of the nighttime and the daytime. So if you see the infrared camera and the visible camera. So visible camera we cannot see on the night, but the infrared camera we can see the contrast. So they're different because, as I said, the property of the material will remain the same whether it is day or night. So depending on the different property, heat capacity, inertia, emissivity, so it is emitting radiations. So every features, whether this feature or the road or the sand or the water, different surfaces will emit different radiation, and depending on this, we can identify it very sharply. It can penetrate to thin clouds. You can see from a aircraft, we can see that it can penetrate to the thin clouds, and we can see to fog also it can penetrate to some extent. You see, it's a thin fog, also it can penetrate. You can see that this is the same figure of the daytime and nighttime, and you see here, this is some of the concrete area, urban area. You see, this is the water body. This is a sea, a deep sea, and this is the shoreline. If we see this daytime, and if you see the nighttime, there is a different contrast. You can see easily this is a shore, this is and this is shoreline, and easily you can see the contrast between because here the white means high temperature, dark black means low temperature. So in the daytime, water is at low temperature, nighttime water is high temperature. Sand is now low temperature, but during daytime sand is at high temperature. So the contrast, from this contrast one can easily identify here as compared to daytime. For example, if you see this area, here there are some parking lots and some vehicles also you can identify in the night time, because the background is concrete and the car or the vehicles are at higher temperature. So we can have a contrast. But during daytime, there are more or less the difference of the temperature between background and the foreground is not much. So that's why it camouflages. We cannot identify easily here. But most of the features we can identify in the night time. So that's the beauty of the thermal sensors, that using the nighttime or the daytime, we can have a contrast of certain features depending on the thermal signatures of that materials. This is the volcano feature. This is the visible infrared. That is the green-blue infrared, and this is the thermal infrared or short wave. So thermal infrared means what happens is this is short wave infrared, because normal features we can identify in 8 to 14 microns, But as the temperature increases, the maximum temperature or the maximum emission happens at the shorter wavelength. So we have to use around 3 to 5 microns. And depending on that is the Wien's law. So maximum temperature, it will shift towards the shorter wavelength. So here we can easily see that this is the vent and these are the smoke, and how lava is being distributed and from which direction it is moving. So which we cannot see in the visible infrared image because of the smoke, because it is covered by thick smoke. Similarly, if you see, this is the border of the US and Canada. So Mount Ontario and Mount Erie, River Erie and River Ontario. So what happens is we see some contrast between these two rivers. It means that this is the variation in the depth, but here there is not much variation in the depth. So that also one can easily visualize from the thermal data. Of course, the ship detection. So how the ships or the oil spills, as I said, I have given some examples. So these are some of the pictorial examples from this is environmental modeling. So different gases, for example, there is a forest fire. So how the forest fire, the emissions of the carbon dioxide or the carbon monoxide or the methane emissions or the nitrous oxide, how it is being emitted, and from the satellite sensor, one can temporarily measure and give the between the different models, one can also forecast it, which area it will influence and how much. Of course, when we talk about the thermal infrared, so their sensors are also different, or the fabrications of the type of the cameras are also different from the visible infrared wavelengths of the cameras. So the thermal infrared detectors are normally composed of the indium antinomide. This is which has a detector sense of 5 microns. And for 8 to 14 microns, we use the mercury doped germanium, which has a sensitivity of 8 to 14 microns, that is peak at 10 microns. And for broad, we use the mercury cadmium telluride, that is 8 to 14 microns. So these are some of the sensors which we use in the satellite sensing. And the problem with this is it has to be cooled down. So there is a because when the radiation strikes on the detectors, so it also raises the temperature of the detectors. So that detector temperature has to be cooled down. So we have a cooling mechanism on board the sensor, which we use the liquid helium or the liquid nitrogen to cool down the temperature. Now, as I said that we use most of the atmospheric windows, but in fact, not all the energy emitted makes through the atmospheric window. So we have to correct for the slight atmospheric correction. So there are different methods for it. One is the ground truth method. So what it happens is it tries to calibrate the space-based measurement, what it measures or the space sensor against the brightness temperature measured at the ground surface. So at the sensor level and at the ground level of different features, and tries to minimize or try to rectify the atmospheric component. Another is the radiative transfer model. So what happens is we on the ground using the radio sound profiles, we have a different parameters of different atmospheric layers. The parameters come on the temperature, water vapor, relative humidity, etc. And then we use the radio transfer model to calculate the atmospheric transmittance and the path radiance, and then try to simulate the corrected emissions. So we use some models for it, which is known as radio transfer model. Another is a multi-angle method. So here what we do is we try to measure the atmospheric transmittance, which is proportional to the path radiance or the path length. So so different path lengths, we depending on the different view angles, we try to estimate the atmospheric transmittance, and then we use the model to correct the atmospheric effect. The fourth one is the split window algorithm. So as the word suggests, the split window, what it means is we use two wavelengths in the thermal infrared, in the same atmospheric window, and then we measure the brightness temperature in two wavelengths, and using this brightness temperature we try to average it out, or we try to use different calibration constants to correct the brightness temperature using the split window, using these two wavelengths. These are some examples of the satellite sensors which are having, apart from visible infrared, they are also having the thermal infrared. This is NOAA AV-HRR, Advanced Very High Resolution Radiometer, which has thermal channels, two thermal channels. So two thermal channels means one thermal channels will give you brightness temperature, another will give you another brightness temperature. So T1 and T2. So using this T1 and T2, using these two wave bands, one can, using the split window technique, we can calculate the actual surface temperature. So that's the concept. The Landsat also Landsat till Landsat 7 we had one thermal channel, but now Landsat 8 we have two thermal channels. So we can use the same split window using this on the Landsat 8. Another sensor which is on the Aster, so Advanced Spaceborne Thermal Emission and Reflectance Radiometer. So it has 15 channels, and 5 channels are devoted only for the thermal infrared, which is in the 8 to 12 micron with a 90-meter resolution. And this has the Landsat has 30-meter resolution, and AV-HRR has 1 kilometer resolution in the thermal infrared. MODIS, that is the Moderate Resolution Imaging Spectroradiometer. So these have 36 channels, and many channels are devoted to thermal infrared from 3 microns to 14 microns. So one can use over the on the Earth surface, as I said, 10 microns, 11 microns. So these 31 and 32, number 31 and 32, which is 10 to 11 and 11 to 12, these channels can be used for sensing over most of the Earth surface features. So why this 10 to 11, 11 to 12? Because of the atmospheric window. So not 8 to 14. 8 to 14 is a broad spectral range, but depending on the atmospheric window, we choose these channels, 10 to 11 and 11 to 12. Then the sensor which is devoted only for the trace gases is MOPIT, which is known as the measurement of the pollution in the troposphere. So it is an 8-channel gas correlation radiometer. This measures mostly the carbon monoxide, and methane as well. The then IIRS, that is Visible Infrared Imaging Radiometer. So it has a series of bands from visible to thermal infrared. So different applications from land, from ocean to atmosphere, and different applications. So if you see the these channels, 3.5 microns. So this is cloud, sea surface temperature, land surface temperature, and the cloud properties. So all these can be used. Then ASTER, this is the Advanced Along Track Scanning Radiometer. So these are having the 7 bands. So 4 in visible infrared, and 3 in middle infrared and thermal infrared with the 1 kilometer resolution. Then IIRS, then this is launched in 2002, and these provide the highly accurate measurement on the air temperature. Most of the atmospheric related parameters like air temperature, humidity, clouds, and some of the trace gases like ozone, carbon dioxide, carbon monoxide, methane, etc. So those particular wavelengths where it is sensitive, or the absorption happens to the sensitiveness of these trace gases. So we use those wave bands. Then especially for the cloud and radiant energy system, the CERES, the cloud and the energy radiant energy system. So it measures the total thermal radiation budget, and also it has 8 to 12 micrometer thermal and infrared band, which is devoted for the surface thermal radiations. Then high resolution dynamics in the limb sounder on board of the Aura satellite. So this is a different kind of one is the nadir view, this is a limb view. So this is slant view type. So it measures the tropospheric temperature and water vapor retrievals, most of the atmospheric retrieval parameters, which is used in various applications. So it has a thermal infrared from 6 to 18 micrometer with a 500 meter resolution. Then tropospheric emission spectrometer, so TES. So it monitors the trace gases like ozone, tropospheric ozone, and with a very high spectral resolution. Of course, this Sentinel series, Sentinel-1, Sentinel-2, they were different series. And Sentinel-3 is devoted for mostly to ocean, this ocean mission, Sentinel 3A and 3B. And it has the thermal channels, because it is also not only for ocean, but also it can be used for the land features. So it has the thermal, especially thermal channel for these kind of parameters. So these were all the Earth observation sensors, and what I showed you all are freely available. So the data, their products are freely available, and one can use and download it. And these are some examples of the geostationary platform. For example, the GOES 16. This is US the geostationary satellite, and it has the advanced baseline imager ABI, that is the sensor, and it has 16 wave bands, and there are specific wave channels for the thermal infrared. So short wave thermal infrared and middle thermal infrared and long wave infrared. So these are, as I said, 6 to 7. These are mostly for the clouds and water and all that, and these 10, 11 and 12, these are for the our ground features. These are Himawari. This is from Japanese, the Japanese satellite, and this also has the similar kind of a wave band as the GOES sounder, GOES. Meteosat. So we can see that this is the European one. This is the Meteosat, the second generation satellite, MSG. So it carries a set of instrumentation. We call it SIVRI, that is a spinning enhanced visible and infrared imager, and it has 12 channels with the infrared channel as well. India has its own INSAT series of satellite, and there are many INSAT series which are used for different applications or environmental, weather, and as well as a Earth observation sensors. So specifically the INSAT 3A, Kalpana 1, and INSAT 3D. INSAT 3D, they are, so in INSAT 3D we have a imager as well as sounder. So 6-channel imager as well as 19-channel sounder. So this is used for the Earth observation features. For example, the sea surface or the land surface or the accidental fires, the forest fires and all that. And this is for the atmospheric profiling or different atmospheric parameters like temperature, humidity, water vapor. And these are some of the earlier glimpses what I have given, and these are the other sensors which are having the thermal infrared in that, embedded in that. So thank you. So